Namaste. Welcome to tutorial series on SuperPro Designer for beginners, step-by-step guide to process simulation. In this tutorial, let us learn how to simulate a ferment procedure or fermentation procedure available in SuperPro Designer. Just for an example, I have taken a simple case of streptomycin production process. When you open this streptomycin production example shipped with SuperPro Designer, it is a very complicated process which is having so many unit procedures and operations. But as we are using demo version of the tool, we are having option of adding only 2 unit operations. From this streptomycin production example, I have just taken this shake flask and the main production fermenter details, and I have set up the problem statement. So I request all of you to go through this particular flow sheet for better understanding, and also you can read the supporting file given along with this example. So now, as a base case, let us understand how to initiate this fermentation process in SuperPro Design. So when you come back to this problem statement, so it says that typical streptomycin production process consists of inoculum development in a shake flask and streptomycin production in a fermenter using a Streptomyces graecosus. The composition of media for inoculum development and main fermenter is given. So both slightly different compositions are there for both the media. And inoculum development was carried out for 2 days at 28 degrees centigrade using 1.5 kg of media. And the bacterial growth is modeled by that particular stoichiometric equation is given, and conversion is given as reaction yield is given as 70%. And also the production of streptomycin is carried out at 28 degrees centigrade in a fermenter, and it is 200 kg of media is used, and that fermenter is operated for 6 days. And mycelial growth and product formation, that particular production is modeled by the given stoichiometric equation, and reaction conversion is given as 98%, and also the heat of reaction for oxygen is given. So let us see how to use this particular data in the simulation stages. And also the aeration is given. As the production process like aerobic process, the continuous oxygen supply is required, and the aeration rate is 0.2 ppm. So now let us start the setting up the process. First, we need to register the pure component. Let us go to task, pure components, and we register them. So here the important requirements are the glucose. So basically the glucose is already available in the database. I'll select glucose and register it. And next one is soya hydrolysate. It is not available in the database. We'll check for soya related component. There is soya flour is there, soya oil is there, soya hydrolysate is not there. So I'll just go and register as a new component as soya hydrolysate, soya hydrolysate. So or else you can even I just registered it as for default properties of water. If you want, you can initiate with again soya flour is there. You can even register with the properties of proteins also. And the next component required is sodium chloride. I'll register with sodium chloride. And next very important thing is ammonium sulfate, which is available. So water anyhow it is already available in the database, like registered as default component. Leave it. And next very important thing is Streptomyces graecosus, that is a biomass. We'll select biomass, and even this biomass we can edit it, that particular local name as Streptomyces graecosus. Streptomyces graecosus. And next, the important component is carbon dioxide. I will select carbon dioxide, and also the product streptomycin need to be registered. It is not available. Streptomycin is not available. Just we go to register as a new component and we register streptomycin. and we go with default water properties. So all the required components we have registered. Media, again you can register it as a stock mixture if required, or else during initiation of streams you can define the composition of media. Let us register in two different ways how we can initiate the streams. Now all the required pure components are registered. So now what I will do, fermentation media, I will register as a stock mixture. Inoculum media, I will just initiate whenever I initiate the shake flask, but fermentation media I will register as a stock mixture. We go to task stock mixture and new stock mixture, and I will register fermentation media with 0 initiated to 0. And now I will change the combination of fermenter media. Go to composition, and ammonium sulfate is there, glucose, sodium chloride, soya hydrolysate, and water. These are the components of the fermentation media, and composition is given here. So the glucose is 20%, ammonium sulfate is 5%, soya hydrolysate is 2%, and water is 72.8, and the sodium chloride is 0.2. So this is the composition of fermenter media. So I'll just click OK based on marks percent I have added. So click OK. If percentage is 100, so it won't show any error. Okay. So now we registered all the pure components required for the simulation, and also we registered fermentation media as a stock mixture. Shake flask media I will directly initiate when I initiate the flask. As per the problem statement, we required two operations. One is shake flask, that is available in inoculum preparation. First we need to prepare the prepare inoculum in a shake flask, and I will simulate shake flask, then I will initiate the fermenter, because if you get any error, it is easy to rectify when you simulate one by one procedure. Now the shake flask is fed with the media, and also you are going to get the inoculum. It's a simple process, and there is no aeration in the shake flask, so 2 streams are sufficient. I'll just rename it as media, and I will rename this as inoculum. And here we need to add the operations, batch process. So we need to add the operations. So simple operation like I need to charge it, I need to react stoichiometry. Here there is no auction involvement is there. That is the reason we can just use the react stoichiometric operation. No need to use the ferment operation. And also we need to transfer it out. So these are the simple operations. Click OK. And let us go to this operation initiation charge. So here in this case I will select this media stream, but one more thing you remember that I have not initiated this media stream. So I will go to this media stream, and then I need to initiate it. That it is it's not active now because here set by user is selected. So that is the reason I will select this as use amount on stream. Click here, and I need to add the composition. So what are the components in the particular inoculum media? That is glucose, ammonium sulfate, soya hydrolysate, and NaCl, and water. These are the components, and we need to select the setting like mass composition is given here, so we can set the mass composition. The overall media amount is 1.5 kg. I'll select 1.5 kg and select the mass composition. So ammonium sulfate is 1.1, and glucose is 20, NaCl is 0.2, and soya hydrolysate is again 1.1, and water is 77.6. So it is now 100%. So 1.5 kg. Click OK. So now you can see it is reflecting here. So media I have charged. So two different ways. The fermentation media I register as stock mixture. Here I have just initiated in the stream itself. Next we go with all these default values. If you want, if you think it is too much process time, we'll just make it as 10 minutes and click next. Next we need to initiate the react operation. So as per the problem statement, this particular inoculum is the production is taking place at 28 degrees centigrade. We use steam as a heating agent, and also reaction time is basically for 2 days. So I will set 2 days as reaction time, and rest all we go with default values. And reaction is very important. Here basically the reaction is 200 glucose, that is glucose gives Streptomyces graeus and this particular water. So the mass basis, it is 200 glucose is giving something around 15 Streptomyces and 185 water. So both the side it is balanced. Click OK. And reaction yield, they say it is 70%. I'll select 70% and click OK. Rest all we go with default values. Click OK. Or the next operation, transfer out operation. And as of now, the transfer out operation set by user. So we will select it as 10 minutes. So rest all we go with the default values, transfer out using this inoculum string. So click OK. So we initiated all the required, fed with all the required details, and let us simulate this one. So there is no error. So we'll just yes, mass and energy balance ended successfully. When you double click on this, you can notice almost mass percent 0.015 kg of Streptomyces is produced in this particular process. And when you take a mass percentage, it is around 1.05% of Streptomyces organism is available. So this is a first step of inoculum development. So once inoculum is developed, let us move to the main fermenter. We go to this unit procedure, go to batch vessel, and we choose the fermenter procedure. So in this fermenter procedure, what are the operations takes place? We need to charge the media, we need to charge the fermentation media, and we need to remove this inoculum, because we need to again transfer the inoculum developed. So I will send it the inoculum here. And also is an aeration process. He says that is 0.2 ppm flow, like air is like at the rate air is supplied. So I need one more stream for supplying air. So we have one output. After post fermentation, that we need to take out the fermentation broth. And one more thing, whenever you supply air continuously, it is very obvious we need to have the vent also. Means continuously the air supplied is to be going out of the fermenter, because in the oxygen present in the air is consumed and nitrogen or other gaseous components present here, it will just go out of the fermenter. And also during the fermentation, you can notice in this stoichiometric equation, CO2 is also generated as one of the byproducts. So that will also kind of removed continuously, that is also escaped through this particular vent port or fermenter off gas port. So we'll just rename this streams. I will rename it as fermentation media, and this one I will rename it as again inoculum. I'll rename this as air, and this will rename it as of gas, fermenter of gas, and this was, I'll name it as broth. So this we rename, and let us initiate this stream. So here again you can add all the components and set the mass flow rates or like mass composition, but in this case we have already registered fermentation media as a stock mixture. I'll select it, and how much we need to fed, it is in the problem statement told it is 200 kg. And inoculum, it is like directly it is, you cannot set it because it is an intermediate stream. Post simulation it will be added, but that we initiate using transfer in operation. And also air is continuously supplied. So again air is a stock mixture, we need to add the air, and we don't know how much air need to be charged. It will be calculated based on the process requirement. So I'll just set it as auto adjust. You can notice it is changed to 100 kg. Later this value will be changed after simulation. So now we go to this operation, add operation. So what are the operations required? One is charge is required, and we need to transfer in the inoculum. So we cannot again charge the inoculum because it is obtaining from the intermediate stream. So we need to transfer in the inoculum, and we need to ferment it. So we need ferment stoichiometric because there is no kinetic information, ferment stoichiometric, and also after fermentation we need to transfer out the contents available in the fermenter. These are the 4 operations, and we go back and initiate this operation, charge operation. So just we'll select the fermentation media stream, user amount on stream, which are already available. There the setup process time, you can set the flow rate also. You can for example, I will set it as something around 10 minutes for media charging, and rest all we go with the default values. Next here, transferring what has to be transferred, this inoculum has to be transferred, and as of now I'll just go with default values of this transferring. Later we will set it up based on the master slave relationship once we generate the GANT chart, because this transferring of in the operation in the fermenter is depend upon the rate at which the inoculum is transferred from this shake flask. So as of now we'll just go with the default values, and later we will see to that. And next very important operation is ferment operation, and it is taking place at 28 degrees centigrade, and you can use chilled water as because during fermentation the heat is generated, metabolic heat that need to be cooled. We can use chilled water as an heating agent. And when you go to reaction, here we need to set the stoichiometric equation. The stoichiometric equation is glucose plus oxygen plus ammonium sulfate that plus soya hydrolysate gives streptomyces greases, and carbon dioxide is produced, streptomycin, and water is produced. So we set this mass coefficient, that is 100, oxygen is 90, 25, and soya hydrolysate is 10. So here it is 15, 115, 20, and 75. So if you could notice, both the side it is balanced. Click OK. And also the enthalpy of the reaction is given, so we will just select it. This is, we have to reaction heat has to be set, so we will just uncheck this one, and you can notice this dialog box appears. So enthalpy is given, that is minus 3700 kilocalories per kg. With respect to oxygen, the rate reference component is oxygen at the temperature 28 degree centigrade. So even you have an option to calculate, if you know the component which is already available in the database, you can even calculate it, but in this case it's already given, so I'll just feed the information. And reaction state conversion, it is 98% conversion, it is given in the problem statement. So rest all we go with the default values. And the next one is transfer out. We need to transfer out 100%, and transfer out we will just keep it as 20 minutes. So basically we fed all the information, but one more thing we forgot, that is we didn't set up the oxygen flow rate. You can notice here in the ferment operation, air is chosen. Once you connected this particular port, air by default it chooses that particular aeration port, because air is recognized, and also we already initiated. And what is the flow rate? It is 0.2 VVM. Click OK. Let us simulate this process. Click OK, and you can see it is mass balance ended successfully. There are no errors, and we can notice in the broth, so basically 3.5 kg of streptomycin is produced. And one more mistake we have done, it is nothing but the reaction fermentation step. By default it is 24 hours, so we need to set it for 6 days. Click OK, and again simulate it. So the simulation is going on, and mass and energy balance ended successfully. Now if you could notice, it is almost 7.8 kg of streptomycin is produced after 6 days. And also if you want to understand how much amount of air is consumed, you can check here. Almost 421 kg per batch of air is consumed. And here also the fermenter off gas, if you notice, it is 431 kg. So it is more compared to the air inlet, because here carbon dioxide is also produced, one of the byproduct during the process. So this is basically a simulation of fermenter operation. And if you want to know the Gantt chart, how this scheduling the overall process are like kind of how these operations are scheduled, you can go to this Gantt operation Gantt chart, and you can notice in this operation Gantt chart all the like both shake flask as well as fermenter, it's starting from time t is equal to 0. It is not correct because still the inoculum is developed. It is no need to switch on your fermenter or no need to start the fermentation operations. So let us schedule them. So any of inoculum case is fine because the 2 or 3 operations are available. Charge is kind of initiated at time t is equal to 0. Once it is charged, the react operation start. Once the reaction is completed, transfer out starts. So this is one after the other. These operations are scheduled. But in case of fermenter, when you go to this charge operation, here we know what rate it is charging, but when this charge should start, so here it is related to beginning of the batch, no, relative to another operation in the another procedure. What is the another procedure? It is shake flask reactor. And what is the procedure? It is the react operation. Once the once the reaction is completed, I need to start this particular process. The charging has to be done. So we cannot start, we cannot charge we cannot wait till this inoculum has been transferred, because once we charge the media, then only we charge the we add the inoculum. So it is basically depend upon the react operation. And when do we need to start, whether we need to initiate this charge operation at the start of the reaction or end of the reaction. Basically end of the reaction. If you select the start of the reaction, then again what will happen, your fermenter will start from time t is equal to 0, got it, or when this reaction start. So it is not necessarily required. So we will select it as end of the reaction. This is what is scheduled. And the next transfer out operation, transfer in operation of this inoculum, it is master slave relationship. What is the sequence? That is match with the procedure, that is fermenter procedure, match with this transfer out operation, because we have all initiated all the components, like all the flow rates there. Click OK, and you can notice the scheduling also. It is you can relative to this particular charge is taking. And the next one, the flow rate, earlier it was just I have initiated as 10 minutes. Now the flow rate is depend upon this particular inoculum of transfer out flow rate. Scheduling, you can notice here, once the charge is completed, then only this transfer out operation is understood. So you basically understand that this is the process time. Here the master slave relationship, whatever you set up, to set up the flow rate of the system. So this flow rate I cannot set it here, because this flow rate is depend upon the transfer out flow rate of the shake flask. And this scheduling by default in this is the second operation in the ferment operation. It is related to this charge operation. And when you go to the next operation, you can notice all the remaining operations are in a sequence to the previous operation. Click OK, and we just simulate it, and we go to this chart operation Gantt chart, and select operation Gantt chart. Let us check whether they are scheduled. Now it is correct. So this is the time required for 48 hours is the inoculum development time, and almost you can notice some 6 days. You can notice it is a fermenter operation. It is charge, react operation, transfer out, and you can notice this transfer out is basically depend upon this transferring of inoculum is basically depend upon this transfer out of flow rate. And once charge is done, then only this transferring is initiated, and this is the ferment operation is carried out, and we have can transferred out fermentation broth. So this is a simple simulation of fermentation equipment available in the SuperPro Designer. I hope you understood how to set up this shake flask and fermenter. In the next tutorial, the same example, the extended version will learn, we can add some fed batch to the system, or feeding the media continuously, basically a fed batch process. And also we can add some cleaning step, before initiating the fermenter, we can add a steam in place process, we need to sterilize the fermenter. Once the sterilization is done, we need to clean the fermenter. Basically it is again a sterilization process using chemicals. And post fermentation, we can again steam in place can be carried out to clean the fermenter. And yes, we can understand the process better. So thank you for watching. Please do not forget to subscribe.